Okay, well, let's take a look at solving some more of these kind of trigonometric equations. So here's one let's examine. Tangent x times sine squared x equals tangent x. Let's solve this and see what values of x will satisfy this. Now, there's a great temptation here to cancel away the tangent x on both sides. That would simplify things. But that would actually, though, lose a whole bunch of solutions. Because, in fact, you can't cancel unless you make sure those things aren't 0. And if these values are actually 0, that's a solution, because 0 equals 0. So, in fact, we have to be a little bit careful. You just can't cancel things away blindly. Better is to factor. So what I'll do is I'm going to bring everything over to the left-hand side and have this thing equal 0. If I do that, what I would see is tangent x times sine squared x minus tangent x equals 0. And now I see a common factor of tangent x here, and I can factor that out. So let's do that. So if I factor that out, I see tangent x times, and what am I left with? Sine squared x, and then here I have a minus 1 equals 0, right? Because if I distribute, that gives me the tangent x here, so that minus 1 is necessary. Okay, well now I have the product of two things equals 0. Well, that means we have two possibilities. Either this equals 0, so either tangent of x equals 0, or this thing equals 0, which means what? It means that sine squared x equals 1, right? That's what it means for this to equal 0. Okay, well, either tangent equals 0, so we've got to find all the places where tangent equals 0, or, and now I guess I could take square roots, but I got to be careful. I have to take plus or minus square roots, and so I'd see sine of x equals plus or minus the square root of 1, which is 1. Okay, so what I see here are a whole bunch of possible solutions, and now I got to figure out exactly where those things occur. So what about, where does tangent equal 0? Well, a little graph of the tangent function should be revealing. So let me graph a tangent function for you really fast. If this is 2 pi, this is pi over 2, pi over 2. This is 2 pi here, minus 2 pi, minus pi, and so forth. Then what I see is we have the asymptote at the half multiples. Oh, shoot. Shoot. Screw that up. Oh, let me do that again. I put the dotted line in the wrong spot. That's okay. No problem. See, the great thing about graphing is that if you make a mistake, you just do it over. It's not a big deal. It's not like, someone's really... Okay, here we go. So I cut it in half. That's pi, half again, half again. Those are the half angles. Do that here. And the asymptotes are going to be here at minus pi over 2, at pi over 2, 3 pi over 2, minus 3 pi over 2. Okay, now we're in good shape. Let's start to graph this function. And all I care about is when it equals 0. Asymptotes here. And it keeps going. Well, where does it equal 0? Well, notice it equals 0 at 0, and then at pi, and then at 2 pi, and then at minus pi, and at minus 2 pi. It's just all the multiples, all the integer multiples of pi. So in fact, this solution here tells me that x equals pi times any n, where n equals 0, or plus or minus 1, or plus or minus 2, and so forth. Any solution will make, in fact, the tangent function 0, which will make this whole thing 0 and satisfy the equation. So there's one solution. But what about where sine of x equals plus or minus 1? Well, let's look at the sine function and ask, where does that equal either plus or minus 1? Well, it equals plus 1 at pi over 2, equals minus 1 at 3 pi over 2, and then it'll equal a plus 1 again. Where? Well, that will be at sort of the next pi over 2 that we'd get, which would be 5 pi over 2, and so forth. So what we see here is we have, as a solution, how could I write this? I could say x here will equal any multiple that is an odd multiple. So let's just say it this way. 2n plus 1 pi over 2, where n again is either 0, plus or minus 1, plus or minus 2, and so forth. Because notice that when I plug in any value for n here, those will give me all the odd numbers. If n were to be 0, I'd get just 1. If n were to be 1, I would get 3 pi over 2. If n were to be 2, I'd get 5 pi over 2. And with the negative numbers, I get those negative odd pi over 2. So in fact, this solution to this equation are all the x's that satisfy this or the x's that satisfy this. So it's a huge solution set. And see how I found it? I just factored like we used to always do and then solve each of these things separately, just thinking about where, in fact, what are all the x's that satisfy each of these things individually. Okay, so there's a solution to this particular equation that involves trig functions. We'll take a look at some more solutions to more trig functions up next.